So in this problem we're going to find the centroidal axes which intersect at the centroid of the shape, and the moments of inertia about the about the x and the y axis, where the x and y axes are defined about the centroid. Now this is a fairly simple shape, and because it's so simple we can use it we can use discrete parts and the principles of parallel axis theorem to solve for the moments of inertia rather than trying to integrate over the area. So first off, in order to do this we need to identify several areas where we can sort of divide this shape up into simple components. And it's fairly straightforward. Obviously this is a composite of three different rectangular areas. And how we divide up those areas is up to us. We could either have a line going here and here, so have one rectangle of a height 120 millimeters and two rectangles of width 90 millimeters. Or, as I've done it in this example, we can divide here, segmented across a location that's parallel to the inside edge of those horizontal chords on this channel section. And then once we do that we can identify our areas, so we'll just hash them in here. And we can call this one shape number 1, and we also have a shape 2 over here. We can call them whichever one we want, it doesn't matter which order. So this is a shape 2. And then at the top we have shape 3. So now we have three simple to analyze shapes. We have three rectangles. And we know that we can find the moment of inertia of the rectangle itself about the rectangle centroidal axis fairly simply. And then using the parallel axis theorem and the local moment of inertia, we can find the moment of inertia is about the entire shape at its centroidal axis. So in order to do that, our first step was, as we just did here, we identified that this consists of three simple shapes. And as we know, the majority of shapes that we're going to deal with in civil engineering are composites of rectangular shapes. Occasionally some other more complicated shapes might show up, but those are rare. And composites of shapes might also include non-rectangular simple shapes such as circles or arcs of a circle. Once we identified that this consists of these three simple shapes, we can say one other thing here. We know from the principle of symmetry that the centroid, or the center of the area, lies on an axis of symmetry. And if we look at the shape, we only have one axis of symmetry, and that's an axis at mid-height. So we can sort of sketch that axis of symmetry in here. Here is this axis of symmetry. And an axis of symmetry is a location about which we could mirror the object. So if we were to fold the paper along this line, the top and the bottom would lie on top of each other. It would be a perfect symmetrical shape there. We can't say the same about an axis in the vertical direction, so this is axial symmetric or singly symmetric shape. This means that we know that the centroid, the center of geometry here, lies somewhere on this axis. And in fact, it's going to lie at a location closer to approximately where my pen is now. And that is because of the, it's really the found with the first moment of areas, so we're balancing the areas on the right and on the left of the centroid. So we can say right now, we'll just draw it in here. We don't have a location for it yet, but we'll call this y, and we'll call this x. We do know where x is, we don't know where y is. So where x is, let's just extend this axis out just a little bit more. And we can say that x is located simply at a height of y bar with respect to this bottom corner. And we can say that y bar is equal to 1/2 the height. And that's from the symmetry. And so we can say that that's equal to 10 plus 100 plus 10 over 2. And this is equal to 60 millimeters. So at this point we know that property. We don't know the location of the x, or sorry, of the y-axis. We don't know x bar relative to a point. So let's define what x bar would be. What we're looking for is going to be a distance between a point on the shape, or a point where we know, or a defined point. So the best defined point here might be this bottom left corner. So between that in the x direction and the y-axis, and we don't need that. So now we need to find, the next step is we need the properties of each component, and this will allow us to find x bar, Ix, and Iy, the moments of inertia about the x and the y axes. And to do that, we can establish a table, and this table simply lists our different shape components, 1, 2, and 3. And then first off, we'll get our areas of each shape. So our first, for component number 1, our area is simply 100 times 10 is equal to 1,000. For component 2, our area is 10 times 100 is equal to 1,000 as well. And component 3 is also equal to 1,000. So we take the height for component 2 and the width is 10. Since the centroidal axes are found using the first moment of the area, we need to find the centroids of each area of each shape. So we have a rectangle here. We need the centroid of the rectangle itself, the centroid of the vertical rectangle, and the centroid of this rectangle here. And we'll use those to then determine the centroid of the entire shape, which lies at x equals 0 and y equals 0. This is shown in this figure how we would locate that for a rectangle, and the centroid is simply equal to half the width or half the height. And this we can see just empirically, we know this to be true, but also we could consider that there's an axis of symmetry in the y and axis of symmetry in the x prime direction, and this would result in a centroid being at the midpoint of this section. So that means that x tilde here, and we'll put it relative to this point, relative to the well, here we define it, x tilde, which would be the centroid of our shape, individual shape component, is relative to the point minus x bar on the x-axis. So if we come to x equals 0, 0, and then go over minus x bar, we're at a point here. And so essentially we're at the far edge of the shape, and at the intersection of the edge of the shape and the x centroidal axis. So we're at this point, and we're going to define x tilde with respect to that point, or really any point on this extreme edge of the shape. So this means that first we're, if we look at shape 1 here, x tilde is simply equal to 100 over 2 is equal to 50. And the shape 2, it's equal to the width over 2 is equal to 5, and shape 3 is 100, oh, not 1,000, 100 over 2, and that's also equal to 50. And then y tilde is the centroid of each subcomponent with respect to the x centroidal axis. So that's defined here. So that means to get to shape 1, we need to go down 50 and then 10 over 2. So we're going to be at minus 100 over 2 minus 10 over 2 is equal to minus 55. To get to the centroid of shape 2, we'll just be at 0. And to get to the centroid of shape 3, we're going to be at 100 over 2 plus 10 over 2 is equal to 55. So once we have this table together, we can then find the quantities we need. We know that area total, the total area of the entire shape, is equal to the sum of the area components. And this is equal to 1,000 plus 1,000 plus 1,000. And that's area total is equal to 3,000 millimeters squared. Now if we're going to take the moments of the areas, we need to take the quantity of x tilde times area for that component. And so for each one, we're going to take area times x tilde and area times y tilde to find our axes. Since we already know our y value, we don't need to follow through with the second thing I said there. So if we look at our equation here, x bar, as we've defined it there, is equal to the sum of x tilde I, area I, divided by area total. So we're taking the sum of each component, product of component and its centroidal axes. And here we can say that we have 50 times 1,000, so this is component 1, plus 5 times 1,000 plus 50 times 1,000, and all that will be divided by our total area of 3,000. So this will give us x bar, as we've defined it in our figure, is equal to plus 35 millimeters. So it's somewhere around the location where we drew it, inside the shape. Now we don't need to find y bar as I stated, but we can prove that yes, that centroidal axis is at 0 location by computing this if we wanted to. And we take sum of y tilde components over area divided by total area, and that would be equal to minus 55 times 1,000 plus 0 times 1,000 plus 55 times 1,000, all over area total 3,000, and this would equal 0 over 3,000. So as we know, y bar is equal to 0 millimeters. and we've already defined that, but this was just a little exercise in case anybody wasn't clear on that. So now I'll just put, we already knew this. So that was just for fun. Now that we have the centroidal axis location, so x bar is equal to 35 millimeters, we're tasked with finding the moments of inertia about the x and the y axes. And that's not too difficult. For that, we're going to use the parallel axis theorem. And in the parallel axis theorem, we can state that the moment of inertia for the global shape, or for each subcomponent, first of all, if we look at a rectangle, we can say I bar x prime is equal to 1 over 12 base times height cubed, and I bar y prime is equal to 1 over 12 base cubed times height. And then later, if we want to determine the moments of inertia about the global x and y system, we can say Ix is equal to the sum of the local, or the component moments of inertia about the component centroidal axes, plus area times the distance between the component axes and the actual centroidal axes. So that's distance in y for x, and that's squared. And Iy is equal to the sum of I bar y prime plus area d distance in x squared. So what we need to know first off is the component moments of inertia about the component centroidal axes, followed by the area, which we know, and then we also need to quantify the distance between the centroidal axis of a shape and the centroidal axis of the entire body here. So if we looked at this top or this bottom piece, it doesn't matter, we'd have a centroidal axis passing through the mid-height of this bottom section, and the distance between that axis and the axes of the entire section would be dy. That would be used in the calculation of component 1 parallel axis theorem. So if we apply that I bar x prime is 1/12 base times height cubed, we can say 1 over 12 times, for section 1, base times height cubed, 100 times 10 cubed, and that would be equal to 100,000 over 12. And if we went to shape number 2, we'd have 1 over 12 times 10 cubed times 100, and this is going to be equal to times, I should rewrite that, I got my numbers mixed up there. For shape number 2, it would be 110 times 100 cubed. So in this case, we would have a moment of inertia in the local or component section of 10 million over 12. And then in component number 3 would be 1 over 12 times 100 times 10 cubed, and this would be 100,000 over 12. And in the end, we'll want to sum all the I bar x components. So we see that we're taking the sum of the local x moment of inertia in x prime and a dy. Well, this is the sum of a sum, so we could break this out and we could say that this is equal to the sum of I bar x prime plus the sum of area d squared y. So we don't need to, finding the sum of all the local moments of inertia is a valuable quantity to us. And if we added all those up, we would see that we'd be at 850,000. Now, we can follow through the same procedure in y, and we'd see that we'd have 1 over 12 times 100 cubed times 10, and this would be equal to our 100,000 over 12. And here we'd have 1 over 12 times 10 cubed. Or sorry, this would be our 10 million. Pardon me. So instead of 100,000, this would be our 10 million over 12 quantity. And this 10 cubed times 100 would equal to 100,000 over 12, and this would be 1/12 of 100 cubed times 10, and this would be 10 million over 12. And then if we were to sum this up, we'd have 1,675,000. We know our areas already are 1,000 for each component, and the sum of that would be 3,000. Now, our distance is in the y direction between the centroidal axis of the component and the centroidal axis of the entire section were already found for us in the previous section. So we know the distance here is 55, and this is minus 55, and the other is 0. So we have minus 55, 0, 55. And then the distance in the x direction, well, we're going to take, starting here, if we want to get to the centroid here, we would have this centroid from this point here is 55, or sorry, from here to here is 50, and from here to here is 35. That means from here to here is 15. And the same with component 3. Now the centroid to component 2 is going to be 35 over, and then coming back 5, so we will be at minus 30 here. Now if we take the product of area times dy squared, this minus 55 gets squared and becomes a positive quantity, and same with this minus 30 later. So we'll fill in this table multiplying area times the square of that quantity, and we'll end up with 3,025,000 and 0 and 3,025,000. If we sum that up, we'd have 6,050,000. And we can do the same for area dx squared, and that would give us 225,000, 900,000, and 225,000. And summing that up, we get 1.35 million. So down here we had the same principle. We could take I bar y prime plus the sum of area dx squared. So if we want to calculate moment of inertia in x for the global, or for the whole composite structure, we would add the quantity, the sum of x bar prime, I bar x prime plus the sum of a dy squared. So this will be 850,000 plus 6,050,000. And this would equal to 6.9 million, 6,900,000 millimeters to the fourth. Now that's a rather large number, and we see that consistently when working with these moments of inertia that we're often of the order 10 to the 6th or 10 to the 9th power. So this is a prime example of where engineering notation is very useful to us, and we could rewrite this as simply 6.9 times 10 to the 6th millimeters to the fourth. And that's a common way of seeing these moments of inertia listed. So we found our one quantity. Now let's find it in the y direction. About the y-axis, I'm sorry. So we'll take the sum of the two values here, I bar y prime and a dx squared. This will be 1,675,000 plus 1,350,000, and that would equal 3,025,000 millimeters to the fourth. And once again, it's very convenient for us to rewrite this in terms of engineering notation. 3.025 times 10 to the sixth millimeters to the fourth. So at that point, we've concluded the example. I'll just state that this engineering notation I brought in at the end because this example wasn't on that quantity or that technique. But you'll find that as you're doing this, and if you were to, say, elect to compute these sums directly in equation form rather than in tabular form here, then you would probably carry over this engineering notation for all of these subquantities as well, to eliminate or at least reduce the possibility of missing a zero or making a simple mistake in transcribing or entering something into your calculator. So carrying over engineering notation into your calculations is also a pretty strong technique to eliminate the possibilities of error or reduce the possibilities.